This last topic is actually beyond the scope of our course, but I still want to talk about it. Okay? So ultimately, we want hash tables that look like this table on the right, that our items are nicely spread out. So we've seen a number of bad examples of hash functions. For example, if you just return 0, that would be bad. It would work, but then every item would end up in bucket 0. One we've seen is returning the first character of a word. For example, cat would give me 3 because that is the value of the first character of the word. But that was also a bad hash function because it means that you'll have collisions for every possible word that have that same first letter. Another example, which we have not seen, is if we just add all the characters together, that won't work out so well. AB would then collide with BA. That's a bad hash function. Example 4 would be, let's treat our strings as a base B number. We spent a lot of time with that idea, and that can be good, but there's some things we have to be aware of. Now, maybe the moral of the story is that writing a good hashcode method can be pretty tricky, but there's some rough rules of thumb. So I'm going to use this analogy to kind of motivate how we write good hash codes. So if you've ever had a hash brown, they look something like this. The way you make them is not cutting your potatoes into little predictable segments and then cooking them. Instead, you shred your potato into a lot of bits, you flip them all around, and you end up with this mash here, or a hash, if you will. So if you just, for example, add up all the characters, like we saw in example 3, that is not nearly random enough. Whereas if we think about multiplying our data by powers of some base, then that's a way of ensuring that all the data gets scrambled together in some vague way into a seemingly random integer. Now I'm being intentionally vague here because we could spend a whole lecture on this, and it's kind of number theory, really, at its heart. So I'm just going to leave it as this kind of hash brown analogy. So let's see a real hash code example in Java. So this is in Java 8 what the hash code for strings looks like. It first looks up a stored hash value. If it has not already been computed, so basically if the stored value is 0, then it will compute it. How does it do it? It treats the string, the current string, as a base 31 number, and then stores the hash value it just computed and then returns it. So there's two big differences. One is it treats the strings as a base 31 number, not base 126, not base 40,000 or whatever. It uses 31. And the reason it's so small is that real hash codes don't care about uniqueness. So a small number is fine. But we'll talk a little bit about why 31 in a bit. The other big difference is that it actually stores the calculated hash code, also known as caching, so that future calls are faster. So that if we then come around a second time and we look up our cached hash value, at that point you'd see that h is not 0. It's already been stored and calculated before, and we would skip having to actually compute the hash code, which would be faster. So let's talk a little bit about how Java's hash code, why it uses 31, compared to what we did when we used 126. So you might argue that 126 seems better. If we ignore overflow, that means that as long as we have ASCII strings, we have a unique representation, which seems better than 31, where there'll be more collisions in theory, right? If we pick 1, we know that's bad. If we pick the number 1 here, that's just basically bad hash code number, example number 3 earlier, which we said was no good. So it seems like big numbers ought to be better. However, if we ignore overflow, we are failing to take into account a particularly bad problem that comes up for base 126. Now I'm only going to be pretty vague here about this, but there's a very major collision problem for base 126. The strings geochronite is the best thing on Earth, flan is the best thing on the Earth, treachery is the best thing on the Earth, and Brazil is the best thing on the Earth. All of those have the same hash code. And the reason is that any string in Java that ends in the last 32 characters has the same hash code if we use base 126. And the reason is because of overflow. And just to give you a vague idea, it's because 126 to the 32nd power, or the 33rd power, or the 34th power, or indeed any positive power greater than 31, will be 0. So in other words, all of the upper characters, that is like B in Brazil, R in Brazil, and so forth, these all effectively get multiplied by 0. If you're curious and you find this kind of interesting, CS61C at Berkeley is the class for you, but it's not something we're going to talk about. But I just wanted to give you that heads up that hash codes can be tricky. Hidden in the choice of base we just made, we just ruined our hash code. So typically, hash code bases will be small primes. Why prime? Well, one reason is it's never even. That avoids the overflow issue that we just saw. And another is that it avoids the issue that our hash code has a bad relationship with the number of buckets. So for example, if the number of buckets if the hash code is a multiple of the number of buckets, then we're going to have a big problem. And you'll see this whenever you do homework 3. We'll explore that issue a little bit. And then why a small number? Well, it's just a lower cost to compute. It could be easier to compute an answer on real computers. Now, a full treatment of hash codes is way beyond what we could possibly do, but I just wanted to raise some potential issues. Now, just very briefly, let's discuss some other little tricks. So trick 1 was using a prime base gives us better randomness. Now, it's not really random, right? I mean, it's a deterministic process, but we get better randomness. Now, let's say we have a collection of items, and each has its own hash code. So we have some kind of like list of items. Well, what we could do in order to compute the hash code of that entire collection is we could iterate through each object in the collection, and then we could take the existing hash code, multiply it by 31, basically elevating it or smearing it or just bringing it up to the next power, and then adding the new item's hash code. And so this approach will work pretty well, though in practice you'll see that occasionally people will only look at the first 2 items. So instead of iterating through a giant collection of 1,000,000 items, maybe you only do the first 100 or something. Another example is what it might look like for a recursive data structure, and this is a little bit pseudocodey, but let's imagine a binary tree hash code, assuming that we have some kind of sentinel leaves where the value is 0. So in that case, the null sentinels would have 0 value, and the way you would compute the hash code would be my current value's hash code plus 31 times the left tree's hash code plus 31 squared times the right tree's hash code. So it's a common kind of trick, but again, a little beyond the scope of what we'll talk about in this class. Okay, so we got a little bit of a taste of what makes a good hash function, and so now we're ready to summarize. Ultimately, what we did today is we built hash tables. The idea is you take some data, you convert it into a hash code using a hash function. The hash code is then reduced to a valid index, and then we store the data that we have into a bucket corresponding to that index. We will always resize when the load factor exceeds some constant, and then as long as the items are spread out nicely, we get constant runtime. So that's all we have for today. That's hash tables in a nutshell, and it's a really nice and beautiful idea that I can nearly guarantee you'll be asked about at some job interview someday if you go into software engineering. So learn it well and enjoy homework 3.